Hello, dear friends. This will be some supplementary information for our webinar, Global Cooling from Plant Transpiration, Mechanisms and Uncertainties. I received many feedbacks from you saying that this scheme of radiative transfer that I was sharing was helpful to some of you. And so I decided just to give you a few details. So, for example, first of all, to acquaint ourselves a little bit more with this approach, with this toy model of radiative transfer, let us try to reproduce the Trenberth diagram with this scheme. So, what we take from Trenberth diagram? We take that there is a total flux of incoming solar radiation, 239 watts per square meter, of which the major part, 161 watts per square meter, comes down to the Earth's surface and is turned to thermal radiation at the Earth's surface. But the other part, you see, 78 watts per square meter, is absorbed by the atmosphere, and we divide it like a little arbitrary between our two layers of greenhouse gases. So these red layers represent greenhouse gases, which have the following property. They absorb all incoming thermal radiation and radiate all energy that they absorb equally up and down. Okay? So this is what about solar radiation, and we also consider sensible heat and latent heat, and let sensible heat transfer to thermal radiation at the first layer and latent heat at the second layer, okay? And we also demand that we have the energy conservation. So there is 239 watts per square meter in and 239 watts per square meter of thermal radiation out, of which we also consider that 22 goes through the spectral window. It means that it goes from the Earth's surface, okay? So you can see 217 and 22. Now, we want to calculate the Earth's surface temperature from these conditions, okay? So what we do? First of all, we say that if the upper layer, this one, radiates 217 watts per square meter up, it also must to do so down, okay? And then we write the balance for this layer, which means that it radiates 2 times 217, and this is the like export, and import is 39 from solar energy, 80 from latent heat, and something from the layer beneath, okay? So we easily calculate that this something is 315. You should check these numbers because I made this video in a hurry, so I could have done some arithmetic errors, but I tried to do my best. So it is 315, okay? And now we go to the second layer, okay? It also emits 315 up, 315 down. And now we can calculate its own energy budget, which is 2 times 315, okay? And there is income 39 from solar energy and 17 from sensible heat. Okay, this is 17 and this is 17. And there is also 217 from the upper layer. Okay, and from this we happily calculate the radiation of the Earth's surface, which turns out to be 357 with the surface temperature 282, which is like, given this crude calculation and discrete assumption of just 2 layers, could be quite a good result compared to what we have in the diagram, which is 396, we have 357, and Earth surface temperature 288, and we have 282. So you can see that we kind of got sensible numbers, and we get like considerable greenhouse effect compared to the like orbital temperature of the Earth, which is 255. Okay, and here you can like play with this scheme using the same idea, and you will find that the surface temperature depends on where this thermal dissipation takes place. Thermal dissipation of what? Thermal dissipation of solar radiation and of non-radiative fluxes. And so the higher they dissipate, so the more they escape the interaction with the greenhouse absorbers beneath, and so the colder the Earth surface becomes. Conversely, the lower they are converted to thermal radiation, the more they interact with the greenhouse, these fluxes interact with the greenhouse gas absorbers, and so the Earth surface is warmer. So we can get an idea of how this works, how non-radiative fluxes and their changes change the Earth's surface temperature. Okay, and all this would be like very, very good, but unfortunately the reality is not as bright as this, and as always it is more complicated. So we have a very important limitation, which has the scientific name of the local thermodynamic equilibrium. But we shouldn't be afraid of this. It is just says that in this equilibrium, these greenhouse gases radiate thermal photons as if they were a black body having a temperature, local air temperature. So they emit in their own spectral intervals, but as if there were a black body here which had the same temperature as the air. Okay, and so now take a look at our picture. We have calculated everything so beautifully, but now we can see that we have fixed the radiation of each layer. Okay, and greenhouse gases are distributed in the atmosphere under the action of gravity. So they have their fixed position, like imagine the upper radiative layers, the upper 100 kilograms of CO2, and they have a specific place in the atmosphere. So in local thermodynamic equilibrium, our picture sets quite a specific gradient of surface temperature. Not surface temperature, but of the vertical profile of air temperature. You see, and we can see that the temperature decreases with height. So here it corresponds to 315 radiation of the black body watts per square meter, and here only to 217. And here you can see the actual mean profile of air temperature in the Earth's atmosphere. And here is from where approximately 5 kilometers from where the Earth radiates to space in this under this assumption. But now imagine, what if this temperature lapse rate that we calculated by specifying where the dissipation of non-radiative fluxes to heat occurs, what if it turns out to be very steep? What will happen? Then, like, if the temperature diminishes very rapidly with altitude, then an air parcel, which will, like, incidentally rise in this atmosphere, will be warmer than there, and there will be strong convection. And this convection will like partially equalize this temperature gradient and makes it smaller. So, and we will see that the vertical distribution of non-radiative fluxes that we have set so nicely and calculated everything, they are not longer like we suppose them to be, but everything has changed because of convection, which brings more heat to all layers. And so we have a problem when we need to calculate everything simultaneously. We need to know how much these greenhouse absorbers emit and where. And so we have another constraint. We need to ensure that the temperature gradient that results from our radiative transfer picture is compatible with atmospheric dynamics. So if you just take time to think a little on this, you will get it easily. So we need another constraint which complicates the problem. And to solve it turns out very difficult, especially for a global scale, and so it's difficult. And that is why there is this convective parameterization, which I was talking about. So it is a simplification which says we will not be calculating all this solving for like for everything, but we will make certain assumption as to how the non-radiative fluxes of energy depend on the vertical temperature profile. And this requires a specification of a critical lapse rate, which is like, can be an unknown magnitude, which will determine how these non-radiative fluxes depend on the vertical temperature gradient. And so, and here we come to the point that I was referring to during the webinar, that radiative forcing from CO2 doubling is non-zero, even if the vertical temperature profile does not change as CO2 doubles. So the accuracy of its calculation is not as critical as it could be for the task of calculating the radiative forcing from CO2. Because take a look here. You see, when we we go from here to here, like doubling of greenhouse gases concentration. you can see that here, compared to here, we have an additional layer of gas, which is in the upper atmosphere. Yes, and so it is indeed cooler, and it emits originally less heat. So the planet begins to warm. And this is how Arrhenius made the first ever estimate of radiative forcing from CO2 doubling from the observed vertical temperature profile. So he didn't consider any changes in this profile. And his idea was that with more CO2, this upper layer from which the atmosphere radiates to space will go up, just because, you see, you add some gas, and so the upper layer becomes higher. And if higher it is colder, then assuming that it radiates according to the temperature, it will radiate less, and so the Earth will begin to warm, okay? So this was the idea, and it will warm until the same lapse rate, with the same lapse rate, the temperature at this higher layer becomes warmer again, such that it again radiates as much as the Earth receives, okay? So, and we can see that this is like sensible, even if the temperature profile does not change. But radiative forcing from vegetation is a different problem, as I said, which is manifested precisely as the change in the vertical temperature profile. Because take a look here. So we have a situation here, and we can have a situation here. So greenhouse gases, their distribution in the first approximation is governed by gravity. So it is so this upper radiative layer, is located at the same altitude here, and here. But we can see, as we discussed, that here we have 2 and warmer Earth, and here we have 1.6 and a colder Earth, which means that if this layer has the same temperature, because so emission to space didn't change, it means that here the temperature lapse, the gradient of temperature is smaller. So the difference in temperature between this height and this height is smaller here than here. Okay? So redistribution of non-radiative fluxes is just proportional to the change in the vertical temperature profile. So any inaccuracy in its calculation will be crucial to this effect, in contrast to the task of calculating CO2 radiative forcing. And if the model with the convective parameterization parameterizes what it is supposed to solve, which means how the vertical temperature gradient will change when we change this, remove the forest, its skill for the problem is by definition 0. So you see, this is just some more details to my statement that CO2 doubling and global cooling from plant transpiration are different problems for which global climate models have fundamentally different skills. Okay, that's it. Thank you very much. And you can now return to the webinar following this link. Okay, stay well.